Hey there, and welcome. If you've ever felt like you need a secret decoder ring just to buy a new computer, you are definitely in the right place. Today, we're pulling back the curtain on all that technical jargon to figure out what it all actually means. Let's dive in.
So I'm sure you've seen something like this, right? An ad just jam-packed with numbers, acronyms, and terms that might as well be written in a totally different language. Intel i7, 32 GB, DDR3 SD RAM, 1 TB SATA. It's just a lot, and honestly, it's kind of designed to be a little intimidating.
So the big question is, what does any of it mean? You see this wall of text and you're just supposed to somehow know what's good and what's not. Well, by the end of this, you will. We're going to crack this code together.
Okay, so before we can really translate that ad, we need to get on the same page about, what a computer is at its core. So in this first section, we're going to cover two fundamental ideas that everything else is built on. First up, let's talk about the difference between computer organization and computer architecture. The easiest way to think about it is like this. Organization is the physical stuff, the actual circuits, the memory chips, the wires. It answers the question, how does it physically work? Architecture, on the other hand, is the logical design. It's the blueprint, the big ideas, dealing with instruction sets and answering, how do I design it to perform tasks?
And what are they designing, really? Well, if you strip away all the bells and whistles, any computer is basically just three things. It needs a processor to run programs, a memory to store those programs and data, and some way to get information in and out. That's input-output, or I/O. Processor, memory, I/O. That's it. That's the whole game right there.
All right, with that foundation laid, we are ready to go. Let's jump into section 2 and actually start cracking the code on that ad, piece by piece. Okay, first, a super quick cheat sheet on the units we're going to see. When you see kilo, mega, giga, and tera for capacity, just think thousand, million, billion, and trillion. Easy. And when you see terms for time, like milli, micro, and nano, just know that we're talking about incredibly tiny fractions of a second. We'll see these pop up as we go.
Let's start right at the top of that ad. Intel i7 quad-core, 3.9 GHz. This part is talking about the microprocessor. This is the absolute brain of the whole operation. It's what's actually running all the programs. So, what does that 3.9 GHz part actually mean?
Well, that brings us to hertz. Basically, a hertz is 1 cycle per second. It's how we measure a processor's clock speed. And modern processors are so ridiculously fast that we measure them in gigahertz. That's GHz, which is billions of cycles per second. The bottom line, a bigger number here usually means a faster, more powerful processor. So that 3.9 gigahertz from the ad, it's not just some random number. It means that processor is performing 3.9 billion, with a B, cycles every single second. Kind of mind-blowing when you think about it, right? Okay, moving down the list, we hit the memory. 32 GB DDR3 SD RAM and 128 kilobytes L1 cache, 2 MB L2 cache. Now don't get hung up on DDR3 SD RAM. Seriously, just think of it like a model number. What we really care about here are RAM and cache. This is the computer's temporary workspace, where it holds everything it's working on right now.
So think of RAM as your whole desk. The more RAM you have, the bigger your desk is, which means you can spread out more projects and multitask without everything getting slow and cluttered. Cache, on the other hand, is a much smaller but super fast memory. It's like the stuff you have literally in your hand or on a sticky note right on your monitor. It's the data you need right now. L1 is just a smaller, faster version of L2.
All right, next up, we've got the 1 terabyte SATA hard drive. Again, that SATA part is just about the connection type. The important thing to know is that this is your long-term storage, and it's totally different from memory. If RAM is your temporary desk space, the hard drive is the big filing cabinet where you keep everything when you're not using it. The size of the hard drive tells you how big your filing cabinet is. That 1 TB, that's 1 terabyte, which as we saw is about 1 trillion bytes of space. And the 7200 RPM, that's just how fast the disk inside is spinning. The faster it spins, the faster your computer can find and pull up your files. Okay. The last major piece of this ad puzzle is that list of ports, 10 USB ports, 1 serial port, and all that. Remember how we said a computer needs a way to get data in and out? Well, this is it. This is how the computer talks to the outside world. So yeah, ports are just the connection points for all your external stuff. Your mouse, your keyboard, your printer. The one we all know is USB, the Universal Serial Bus, and its killer feature is plug and play.
which, we totally take for granted now, but it just means the computer automatically figures out what you plugged in. It's a game changer.
And there you have it. We've actually decoded the ad. But here's the next question. How do all these physical parts, the processor, the memory, all of it, how do they actually work with the software, with the stuff you click on every day? Let's find out. In our next section, we'll see how a simple mouse click turns into an electrical signal.
This right here is the computer-level hierarchy. The best way to understand it is to think of it like a stack of translations. Each layer is just a simplified way of looking at the much more complex layer right below it. It's a ladder of abstraction, from you at the very top all the way down to the physical wires at the bottom.
So let's follow the journey of a single command, okay? It all starts with you at the top. You click an icon. That action is understood by a high-level programming language, like Java. Then, that code gets translated down into a language the machine can understand, which the operating system manages. And then, it's translated again into the specific machine code for your computer's architecture. And finally, at the very bottom, level 0, the physical circuits and gates fire electrical pulses to do the actual work. It's this incredible cascade that happens literally way faster than the blink of an eye.
So, that's how our computers work right now. But what about the future? For our last section, let's look at two huge forces that are shaping the future of every single component we just talked about.
It all boils down to this epic battle between two laws. On one side, you've got Moore's law. This basically says that the power of computer chips, the number of transistors we can cram on there, doubles roughly every 2 years. More power, same amount of space. But on the other side, you have Rock's law. It says the cost to actually build the factories that make these super powerful chips, that doubles every 4 years.
And you can see the problem, right? This creates this huge tension. We're getting way better at making chips more powerful, but it's getting astronomically more expensive to do it. Basically, for Moore's law to keep going, Rock's law has to break. They can't both go on forever. Something's got to give. So that leaves us with the big, multi-trillion-dollar question for the future. Which law breaks first? Will we run into a wall of physics where we just can't make transistors any smaller, breaking Moore's law? Or will it just become too insanely expensive to even try, and the economics of Rock's law bring progress to a halt? It's a really fascinating problem, and the answer is going to define the next generation of, well, everything we use. Thanks for tuning in.